All right, let's get started. Today, we're going to level up from basic if-else error checks and really dive into a core feature of professional C++ development, exception handling. This, right here, is what separates code that just kinda works from code that is truly robust and resilient.
So here's what we're going to cover. First, we'll talk about why we even need exceptions. Then we'll get into the nuts and bolts, the try, catch, and throw. After that, we'll see how to handle different kinds of errors, how to make our own custom exceptions, and then we'll hit the really crucial topic of writing exception-safe code, wrapping up with some key principles for making your software rock solid.
Okay, so first things first, why bother with exceptions at all? Well, it's all about getting away from that tangled mess of old-school error handling and moving toward a much cleaner separation of what your code is supposed to do versus how it handles things when they go wrong.
If you've ever seen older code, you know what I'm talking about. Error handling was just mixed right in with the main logic, creating this awful spaghetti code. And the worst part? Those error codes could be super easy to just ignore, which leads to silent, really dangerous failures down the line. Exceptions totally fix this. Think of your main code as a clean highway. Exceptions are the well-marked, unmissable exit ramps for when things go wrong. You can't ignore them. They force the code that called your function to deal with the problem, making sure that errors are clearly passed up the chain until somebody handles them.
So, the whole system of exception handling in C++ really comes down to three key players: try, catch, and throw. Let's meet the team. First up is the try block. The easiest way to think about this is as a designated watch zone. You wrap any code that you think might cause a problem inside these curly braces. It's basically you telling the compiler, hey, keep an eye on this section for me, something might happen here. Next, we've got the throw statement. This is your signal flare. The moment your code detects an error, a file isn't found, the input is garbage, it uses throw to launch an exception object into the air. It's a big, loud signal that something has officially gone wrong. And that brings us to the catch block. This is your specialized response unit. It just sits there, waiting. And if a throw statement sends up a signal flare that it recognizes, it swoops in, catches it, and runs the code inside. This is where you actually deal with the problem. You log the error, you clean up, or maybe you try to recover. So let's put it all together. Your code is running along inside the try block. Suddenly, a throw gets triggered. The second that happens, execution of the try block stops dead. And then a super important process called stack unwinding kicks in. This means any local objects that were created inside that try block are automatically and safely destroyed. The program then travels up the call stack looking for a catch block that can handle this specific type of exception. It's a process that guarantees a clean, orderly exit from the local scope. But of course, not all errors are the same, right? A file not found error is totally different from a weird math logic error. C++ has a really powerful way for us to manage all of this complexity, and it uses the class hierarchy and polymorphism to do it. See, at the very top of the standard library's hierarchy, we have std exception. Everything else comes from this. And underneath it, you get more specific categories, like std logic error, which is for bugs in your program's logic, and std runtime error, which is for stuff that happens while the program is running, like a network connection dropping. This hierarchy is great because it lets us write catch blocks that are super specific or really general, catching pretty much any standard problem. And this brings us to a super critical rule. You have got to put the catch blocks for your more specific exceptions before the ones for the more general base classes. Why? Well, think about it. If you try to catch the base standard exception first, it's going to match every single standard exception. Your more specific, more useful handlers that you wrote for runtime error, they'll never even get a chance to run. Now, the standard exceptions are great, but for real-world professional applications, you're almost always going to want to create your own. This lets you pack a ton of rich, context-specific info right into your error objects. Let's see how it's done.
It's actually way easier than you might think. First, you just create a class that inherits from std exception. That makes sure it plays nicely with the whole C++ exception system. Second, you override the what method to return your own custom error message. And third, and this is the really powerful part, you can add any custom data you want to your exception class. Error codes, file names, timestamps, you name it. This makes your debugging and your logging about 1,000,000 times more effective.
Okay, now we're getting into the real heart of professional C++, exception safety. It's not enough to just catch errors. It's about making promises or guarantees about what state your program will be in if an error happens. The #1 goal is to never, ever leave your data in a broken or corrupted state.
The highest level of promise you can make is the strong guarantee. This is the all-or-nothing promise. It says that if an operation fails and throws an exception, the state of your program is rolled back completely. It's as if the operation never even started. This is perfect for things that have to be atomic, like a bank transaction.
A more practical promise for most code is the basic guarantee. This says that if an exception happens, two things are true. 1, no resources will be leaked, so no memory leaks, no open files left hanging. And 2, all of your objects will be left in a valid, usable state. The operation itself might have failed, but your program as a whole is still stable and won't crash.
And finally, there's the no-throw guarantee. In modern C++, you'll see this marked with the no-except keyword. It's a rock-solid promise that a function will never, ever throw an exception. This is absolutely essential for fundamental cleanup operations, things like destructors or move constructors. Now, while the strong guarantee sounds amazing, it can be really hard and expensive to implement everywhere. And that's why, for the vast majority of your code, the basic guarantee should be your target. It's the minimum acceptable standard. It ensures your application stays stable and doesn't leak resources. And that's really the foundation of any resilient piece of software.
So, to actually achieve these guarantees, you have to follow a few rules that are pretty much non-negotiable. Let's go over the absolute essential do's and don'ts for building C++ code that can take a punch.
First, last, and always, use RAII. That stands for Resource Acquisition is Initialization, and it is hands down the most important idiom in all of C++. The idea is simple. You wrap any resource, a file, a database connection, a lock, inside an object. When that object's lifetime ends, either because it goes out of scope normally or because an exception is unwinding the stack, its destructor is automatically called. And in that destructor, you release the resource. It makes resource management automatic and exception safe. It's brilliant.
And on the flip side, here is the absolute don't. Never, ever, ever throw an exception from a destructor. Just don't do it. Why? Well, imagine an exception is already flying through the air, and the stack is unwinding. If a destructor that gets called during that cleanup process tries to throw another exception, your program is now in a double exception state, and C++ has exactly one way to handle that: std.terminate. Your program is done instantly.
Here's a quick pro tip for both correctness and efficiency. The rule of thumb is throw by value, but catch by reference. Throwing by value makes a safe copy of your exception object. But you want to catch by reference, specifically const_tn, to avoid making another unnecessary copy. More importantly, it prevents a nasty problem called object slicing, where if you catch by value, you might accidentally slice off all the custom data from your derived exception, leaving you with just the generic base class. You lose all that valuable context you worked so hard to add.
Okay, let's bring it all home. What are the big takeaways? 1. Use try and catch to get a clean separation between your business logic and your error handling. 2. Make RAI your best friend. It's the key to resource integrity. 3. Use polymorphism to handle different errors with different levels of precision. And finally, number 4, always be thinking about those exception safety guarantees. Aim for at least the basic guarantee in your code.
And that's a wrap. I want to leave you with this one question to think about the next time you're working on a project. It's pretty easy to write code that works when everything goes right, the happy path, as we call it. But the real mark of a professional is writing code that behaves correctly, safely, and predictably, even when things go completely wrong. So ask yourself, is your code just working, or is it truly resilient?